Alright, welcome to Brunei Math Club. In this video, we study how to compose linear transformations. Okay, let's start. First of all, suppose we have two maps, f from x to y and g from y to z. So there are three sets, x, y, z. And f is from x to y, and g is from y to z. Now we want to compose these two maps. So pick one element from here, from x, then that is mapped to some element in y, lowercase y, which is then mapped to an element z in the set z. So in this case, we can write so y is equal to f of x and z is equal to g of y. So if we plug this y into here, this can be written as g of f of x. So this defines a new map from x to z, right? So this new map is called the composition of g and f. And we write it as g after f. So this is a new map. Okay. So g after f of x is the new map. We can represent this situation in a diagram. Let's say x and y, we have this map f, and from y to z, we have map g. And if we compose this, first f, then g, then we have a new map directly from x to z that is called g circle, f red, g after f. Okay. Let's see an example. We consider two functions. F of x is equal to 3x minus 1 and g of x is, let's say, x squared plus 1. So these are both from real numbers to real numbers, and g is also from real numbers to real numbers. So they are actually transformations, but anyway, the maps are functions are maps and transformations are maps. And since the domains and codomains of both functions are the same, we can compose in two ways, f after g and g after f. So what are they? Let's find out. First, let's consider f after g. Okay, so if we apply this composition, compose function to some real number x, then this is defined as f of g of x. So if we apply g first, then that is x squared plus 1, so x squared plus 1. Then apply f to this whole thing, that is 3x minus 1, so 3 x squared plus 1 minus 1. So that is 3x squared, and 3 minus 1 is 2. So this is the function f after g. Okay, next, g after f. So that is defined as g of f of x. So first we apply f of x, that is 3x minus 1. So 3x minus 1. Then apply g to this whole thing. And g is x squared plus 1. So 3x minus 1 squared plus 1. And if we expand this, that is 9x squared and minus 6x plus 1 plus 1. So that's plus 2. So depending on the order of composition, the two functions are different in general. Next, let's consider two linear transformations on X. Okay. So suppose f transforms point P of xy to P prime x prime y prime, and that linear transformation G transforms P prime to P double prime. Then if we compose G after F, so G after F, that becomes x double prime, y double prime, right? Now, if the matrix representing this transformation F is A and the matrix for G is B, then we have the following. First, x prime, y prime is equal to matrix A times xy. And x double prime, y double prime is equal to matrix B times x prime and y prime. So if we combine these, then we have x double prime, y double prime is B and A xy. And we have BA xy. So here we use the matrix product. So B times A, which we will define later in later videos. But anyway, the matrix composition of two linear maps can be represented by a matrix product. So what this product looks like is the following. Let's see an example. Let's see. So let's say we have two maps represented by these matrices. A, 1, 1, 2, minus 1, and B, 2, minus 1, minus 5, 3. So that means x prime, y prime, A times xy. So A is this matrix. So that becomes, let's say, x plus y to x minus y. And x double prime, y double prime, B, x prime, y prime is, let's see, 2x prime minus y prime and minus 5x prime plus 3y prime. So let's put these x prime and y prime into this expression. So that becomes 2, let's see, x plus y minus 2x minus y and minus 5x plus y plus 3, 2x minus y. Let's expand and tidy up. 2x minus 2x, that's 0x, and 2y plus y, that's 3y. And minus 5 plus 6 is x, and minus 5 minus 3, that's minus 8y. So in the matrix form, this would be 0, 3, 1, minus 8, negative 8, x, and y. So this would be the matrix product B times A. So whatever the values of x and y are, we always have matrix product BA as this one if the matrices A and B are this and this respectively. So B times A is equal to 2 minus 1 minus 5, 3 times 1, 1, 2 minus 1 is equal to this matrix. So how do we get that? If we trace what we did here and here and here, this is like this: 2 times 1 and plus -1 times this 2, and 2 times 1 plus -1 times -1, and -5 times 1. So this times this plus this times this, and 1, 3 times 2, and -5 times 1, this times this plus this times this, and 3 times -1. So this is 0, and this is 2 plus 1 is 3, and -5 plus 6 is 1, -5, -3, that's -8. So this is it: 0, 3, 1, -8. 0, 3, 1, -8. So that's how we get the matrix product. Here we composed B times A in this order, but you should try calculating A times B. So that is, what was A was 1, 1, 2, -1, and B is 2, -1, -5, 3. And you should try to find that this is equal to, let's see, 1, 2, -3, and -1 plus 2, and this is 2, 4, 9, -2, -3, -5. So that's, you should try this. Next, we want to see how to compose 3 maps. But before that, we need to define what we mean by equal maps. Okay, 2 maps are equal. So let's say we have 2 maps, F and G, say from X to Y. And for these 2 maps to be equal, first of all, their domains and codomains should match, of course. Otherwise, they are totally different maps. So that's the first condition. And second condition is, for every element x in the domain, f of x is equal to g of x. If this holds, then we say these 2 maps, f and g, are equal, and we write f is equal to g. Okay, now this is different from writing f of x is equal to f of g of x. This is the equality of 2 elements in the codomain, right? So this belongs to y, and this belongs to y. So these are 2 elements of y, and they happen to be equal. This one is about the entire maps, right? It's not for specific elements. It's an equality between maps. Okay, now suppose we have 3 maps. Let's see, x to y to z to let's say u. So map f, g, h. So 3 maps, f, g, h. For these 3 maps, we want to compose this. So if we pick one element in x, then by applying f, we get f of x, and to which, if we apply g, then we have g of f of x, to which we apply the map H. Then we have H of G of f of x. So what we did is we mapped this element x to f of x to g of f of x to h of g of f of x. So first we composed g after f, and then to that we applied h after g after f. So this is g after f of x, and this is h after g after f. So this is one way to compose. But there is another way to compose. That is, first we compose h after g, then f of x. Okay, so this is h after g of f of x. But what this means is that h of g of f of x, so this is actually the same as this one, which is this one. So in this way we get this map, and in this way we get the same map. So they are actually equal maps. So h after g after f is equal to h after g after f. So this equality holds. This means composition of maps is associative, just like addition or multiplication of real numbers. Diagrammatically, this can be written as, so x to y by f and y to z by g and z to u by h. So if we first compose g after f, then we get this arrow, g after f. Then after this we apply h. Then for this map we get, this one is h after g after f. And on the other hand, first we go this way to get h after g, and then we first apply this and this, then we get this arrow, that is h after g after f. So irrespective of the path going from x to u, this way, they are the same. So in this case, we say this diagram commutes. Okay, this way, it doesn't matter, showing that map composition is associative. And since map composition is associative, the order of composition doesn't matter, so we can safely drop this parenthesis and write this is equal to h after g after f to mean either this or this. They are the same. Okay, that's all for this video. See you later. Bye. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.